Picture this: a single iron atom drifting through absolute darkness. No stars, no light, no heat except a faint background glow barely above absolute zero. This atom will never interact with anything else. It is, for all practical purposes, the only thing remaining in the observable universe, and it will stay this way forever. This is how everything ends, not in fire, not in ice, not in collision or catastrophe, but in an eternal, silent, unchanging nothing. The same law that explains why your coffee gets cold explains why this ending is inevitable. You've been watching it happen your entire life. Here's the principle that seals the fate of everything. Energy spreads out. Heat flows from hot to cold. Concentrated energy disperses. Order decays into disorder. This isn't a tendency or a suggestion. It's a fundamental law of physics called the second law of thermodynamics, and it cannot be violated, not by any technology, not by any civilization, not by any god. Every process you've ever witnessed, every fire that burned, every breath you took, every thought flickering through your brain has been energy spreading from concentrated to dispersed, from useful to useless, from order to chaos. The universe began in an extraordinarily ordered state. It has been running downhill ever since, and there's no climbing back up. This single principle explains why time moves forward, why you age, why stars die, and why the cosmos itself has an expiration date. Follow the second law far enough into the future, and you arrive at a state where energy has spread so completely, so uniformly, that nothing can ever happen again. Physicists call this the heat death of the universe. The story begins in the steam-powered factories of 19th-century France. A young engineer named Sadi Carnot wanted to understand something practical. What's the maximum efficiency you could ever squeeze from a steam engine? This wasn't philosophy. This was industrial power, national competitiveness, money. Carnot discovered something troubling. No matter how perfectly you built your engine, some energy always escaped as waste heat. Always. This wasn't an engineering failure to be solved. It was a fundamental limit written into the laws of nature themselves. Decades later, Rudolf Clausius gave this limit a name: entropy. And Ludwig Boltzmann, an Austrian physicist working in the 1870s, asked the dangerous question that gave entropy its teeth. Why does heat flow from hot to cold? Why never the reverse? The answer seems obvious, except that at the level of individual atoms, physics works equally well in both directions. Film a single atom bouncing off another and play it backward. You cannot tell which direction is forward. The fundamental laws don't care about time's arrow. Boltzmann's insight was statistical. A hot object has overwhelmingly more ways to spread its energy than to concentrate it. When cream pours into coffee, there are astronomically more arrangements where the cream mixes throughout than where it stays in a neat blob. The system doesn't want to mix, it's just overwhelmingly more probable that it will. Boltzmann captured this with a single equation, now carved on his tombstone: S equals K log W. Entropy, that quantity called S, is proportional to the number of ways a system can be arranged while looking the same from the outside. And because there are almost always more disordered arrangements than ordered ones, entropy tends to increase. That word tends is doing enormous work. For a handful of atoms, entropy might occasionally decrease by chance. Cream might spontaneously unmix itself. But for anything of ordinary size, the numbers become absurd. The probability of your coffee spontaneously becoming hotter while the room gets colder is not zero, but it's so small that if you wrote it as a decimal, you'd run out of atoms in the observable universe before you ran out of zeros after the decimal point. This is why the second law isn't enforced by any cosmic police, it's enforced by mathematics itself. Given enough particles, entropy increase isn't just likely, it's essentially certain. The great physicist James Clerk Maxwell tried to find a loophole. He imagined a tiny demon stationed at a door between two chambers of gas. The demon watches molecules approach and opens the door only for fast-moving ones, letting them pass to one side. Slowly, one chamber heats up, the other cools down. Entropy decreases. The second law appears violated. It took decades to understand why Maxwell's demon fails. The demon has to observe each molecule, store that information, and eventually erase its memory to make room for new observations. That erasure, that clearing of information itself produces entropy. When you do the full accounting, the demon generates more entropy than it eliminates. The second law survives. Information, it turns out, is physical. Erasing a bit of data releases heat. Remembering things costs energy. The universe keeps its books balanced. But this raises a profound puzzle. If entropy always increases, if order always decays, then the universe must have started in an extraordinarily low entropy state. Where did that primordial order come from? And what happens when it finally runs out? The Big Bang was, paradoxically, the lowest entropy state the cosmos has ever been in. Not because it was cold and still, it was unimaginably hot and dense, but because gravity hadn't yet done its work. Here's what that means. When matter is spread evenly throughout space, like the near-uniform plasma of the early universe, entropy is low from gravity's perspective. Gravity wants to clump matter together. It wants collapse. It wants black holes eventually, because black holes turn out to be the highest entropy objects in existence. So the history of the cosmos becomes a story of entropy increase, even distributions becoming clumpy, clumps collapsing into stars, stars fusing lighter elements into heavier ones, eventually dying and spreading that processed material back into space to form new generations of stars and planets. Stars, in this picture, are temporary entropy reduction machines. They take dispersed hydrogen and concentrate it using gravity. They create complex structures, fusion cores, layered atmospheres, orbiting planets, and eventually life. But they're not violating the second law, they're just routing entropy elsewhere. Stars radiate enormous amounts of heat into space. The entropy they export far exceeds the local order they create. You exist because stars are exporting their entropy into the cosmic void. The sunlight that powers Earth's biosphere carries entropy away into space, leaving behind the concentrated energy that ecosystems run on. Life doesn't fight the second law, it surfs the entropy gradient created by stellar radiation. Eventually, every star runs out of fuel. The fusion reactions that hold it up against gravity's crush, those stop. What happens next depends on mass. Smaller stars fade to white dwarfs, dense balls of carbon and oxygen, slowly cooling over trillions of years until they crystallize into cosmic diamonds. Larger stars explode as supernovae, leaving behind neutron stars, matter compressed so tightly that a teaspoon weighs 1 billion tons, or black holes. But all of them eventually go dark. In roughly 100 trillion years, that's a 1 with 14 zeros after it, the last stars in the universe will burn out. The cosmos will enter what cosmologists call the degenerate era. A universe populated only by cold stellar remnants, slowly cooling toward absolute zero. No new stars will form because gas clouds will have long since dispersed or collapsed. But even that isn't the end. Jacob Bekenstein proposed something shocking in 1972. Black holes have entropy, and not just a little. A black hole with the mass of the Sun contains more entropy than all the ordinary matter in the observable universe combined. Black holes are where entropy goes to maximize. They're the ultimate disordered states, even though they look perfectly simple from the outside. For decades, it seemed black holes might be eternal endpoints, entropy graves where matter and energy go to rest forever. Then Stephen Hawking demonstrated they're not eternal at all. Through a quirk of quantum mechanics near the event horizon, black holes slowly radiate particles and lose mass. They evaporate. A black hole with the mass of the Sun takes 10 to the 67th years to evaporate. A supermassive black hole at the heart of a galaxy takes 10 to the 100th years. These numbers annihilate human intuition. The current age of the universe, 14 billion years, is a rounding error compared to these timescales. But eventually, given enough time, even the largest black holes will be gone. This principle also explains something deeply personal, why you remember yesterday but not tomorrow. Memory requires physical records, neural patterns in your brain, words in a journal, fossils in rock. Creating a record always increases entropy somewhere. Your brain heats up when you form memories. Ink spreads across paper when you write. The physical process of recording information generates disorder. You can only form memories in the direction entropy increases. That's why time has a direction at all, not because the fundamental laws require it, but because the early universe happened to have low entropy, and everything since has been running downhill from that starting point. The arrow of time isn't written into physics. It emerges from initial conditions and the second law. Every moment you're experiencing the universe running down. The direction you call forward is simply the direction in which entropy grows. So here's the full timeline, running the clock as far as physics allows. Right now, within a cosmic instant of now, stars still burn, energy gradients persist, life and complexity flourish in small pockets. In 5 billion years, the Sun exhausts its hydrogen core and swells into a red giant, consuming Mercury and Venus, scorching Earth into sterility. Life here ends, but elsewhere in the universe, stars continue burning. In 100 trillion years, the last star anywhere, probably a dim red dwarf squeezing the last fusion reactions from its meager fuel, burns out. From that moment forward, no new light. The universe goes permanently dark, except for the faint glow of cooling remnants. Over the following 10 to the 40th years, protons may decay, if certain theoretical predictions prove correct. If they do, the very atoms that made up stars and planets slowly dissolve into radiation and lighter particles. White dwarfs evaporate, neutron stars vanish. If protons don't decay, these remnants remain as frozen iron spheres, but nothing interesting ever happens to them. By 10 to the 100th years, even the largest black holes have radiated away. What remains is a thin soup of particles, photons, electrons, positrons, spread so thin that the distance between any two particles exceeds what the observable universe measures today. Temperature everywhere approaches absolute zero. Energy has spread as uniformly as the laws of physics allow. And then, Nothing happens ever again. This is the heat death of the universe, not a dramatic ending, a quiet one. Entropy has reached maximum. No energy gradients remain to drive any process. No hot and cold, no high and low, no concentrated and dispersed. Without differences, nothing flows. Without flow, nothing changes. Time loses all meaning when nothing happens to mark its passage. And here's the strange thing. Right now, in this moment, the universe is young. This era, the stelliferous era, the age of stars, is a brief flicker at the very beginning of cosmic history. If the full timeline from now to heat death were a 1,000-page book, everything that has happened so far, all of human history, all of life on Earth, all the stars you've ever seen in the night sky, would fit in a fraction of the first letter on the first page. You exist in a vanishingly rare window where complexity is possible, where energy hasn't yet spread out so completely that interesting structures cannot form. The second law guarantees this window will close. There's something clarifying about this, not depressing, clarifying. Every sunset, every conversation, every fleeting moment of warmth and complexity and consciousness is borrowed from a finite budget. The universe didn't have to allow structures like galaxies, stars, and thinking minds. It does, for now, because entropy hasn't finished its work, but it will. Some physicists find this troubling, others find it beautiful, a reminder that the existence of anything interesting at all is extraordinarily improbable, extraordinarily temporary, and therefore extraordinarily precious. The same law that says your coffee will cool says that eventually all the fires will go out. But between the low entropy beginning and the high entropy end, there's time, there's now. There's you, briefly ordered, briefly aware, asking what it means to exist in a universe that's winding down. That question, what does it mean, might be the most complex structure the universe ever produces. And it can only be asked while the stars are still on. If this was interesting, hit the subscribe for more and turn that notification bell on.